Welcome to the Iter Talks. This is the first in what we hope will be an extended series of discussions on fusion and the Iter project, and hopefully for a public audience and widely disseminated. First of all, my task will be to give you the introduction to Iter, where we say it is opening the way to a new energy future. Here you can see the Iter site, the overview of the Iter site. You can see that the site is about 1 kilometer long and about 400 meters wide. You see in the very center the large building, the tokamak building with the assembly hall as a unit. You see in the foreground the Iter heating systems. All the way in the very, very back, you see the electrical switchyard. And along the far side, you see a few of the factories where components that are too big to ship are being manufactured here on site. We'll get into much more of those details. But before we do, I want to talk a little bit about the logic, about why Iter, why have all these countries come together to build this magnificent research machine? Why are they spending the money? Why are they investing in fusion? So the first is really quite obvious. We have a gigantic dilemma related to the need for clean energy. We know that electricity is the vector of civilization. It's civilizational development. We know that we have about 1.6 billion humans that are still not even connected to the grid. And we see constantly statistics about what we can expect by 2030 or 2050 in terms of the additional need for more energy to fuel our lifestyles and our needs. We want to become more efficient, but we also know that electricity has a direct relationship to development. And so the question is, how do we do that? We also know that the use of fossil fuels is having a huge impact on our planet because the waste from fossil fuels goes directly into the atmosphere. So the question that we really have is, how do we meet a vision in which we decarbonize the production of electricity and actually pave the way for using electricity and other clean end uses in a much, much greater way than is used today? So how do we fuel an energy transition? There are only a few solutions. Renewables have been increasingly manufactured and put into deployment in some countries more than others, but the use of renewables is ramping up. So why isn't that enough? The issue is that they are intermittent, and they are, in other words, the sun only shines part of the time, the wind only blows part of the time, but also, much more importantly, they are a low power density because, in effect, renewables are coming from fusion. They are coming from solar energy, but at a distance of the distance between Earth and the sun, and so automatically, the diffuseness of that means that there will be limitations for how we use renewables to power industry or mega cities or other highly intensive energy uses. Fission, nuclear fission, which is really all of the nuclear power plants that are out there today, more than 400 globally, they have issues associated with national policies, associated with safety concerns, associated with waste disposal. And not to go into that too much, but fusion, while it is also a nuclear reaction, hydrogen fusion has inherent advantages that we're going to talk about that make it a very promising solution as an alternative. So what are those advantages? First of all, fusion has the capability, unlike renewables, to be baseload power. It is not intermittent as we envision it in a magnetic fusion device. We'll talk about Iter and the machines that will follow, but fusion has the advantage of actually being a versatile replacement for fossil fuels, available all the time, day or night, and able to supply that intensity of energy that you need for your larger loads. It is carbon-free, meaning that it does not release carbon or CO2 or any other greenhouse gases to the atmosphere. The fuel for fusion is abundant. There are two key characteristics of that. One is that we have, you'll hear in a moment, we talk about two forms of hydrogen, deuterium and tritium. Deuterium is found in seawater, which means it is largely available to really all the countries of the world. And tritium is bred, we envision breeding it from lithiums. And lithium is also readily available in the Earth's crust. So the idea is that if we can master fusion, we really have fuel for tens of millions, maybe hundreds of millions of years, well into the future of planet Earth. Fusion is safe, whereas fission consists of a chain reaction, which if it's too high, creates a runaway. If it's not high enough, it doesn't work. Fission has to be maintained at just that critical element of a chain reaction with a buildup of heat, that if you lose the power to take away the heat, you can end up with a Chernobyl or a 3 Mile Island, Fukushima. So fusion does not have that characteristic. Fusion is inherently safe. It's very hard to do, but if any element of the fusion reaction is interrupted, it simply stops. It shuts down. There's no decay heat. There is no possibility of a meltdown. The only type of accident you could have would be much more minor, nothing that would require evacuation. And the inventory of radionuclides in terms of what would be released is very uniform. It's tritium. So fusion has that advantage. It also has the advantage of being economic in a couple of ways. When it comes to the actual cents per kilowatt hour, that's usually how we compare different types of energy sources. In that sense, we envision it being similar to nuclear fission plants, where there will be a large capital outlay followed by negligible fuel costs in the case of fusion, and very little, relatively low operating costs. However, there's another aspect of economics, two aspects of economics that are not always talked about. One is that when you consider the waste issue, as opposed to fission, nuclear fission, which has tens of thousands of years of nuclear waste to be managed, stored, etc., in long-lived, highly radioactive waste, fusion will not have that. The fusion waste, while you have some tritiated waste from the tritium used, in essence, the fusion radioactive products are simply the activation of the metal itself that surrounds. And that will be relatively short-lived. If you look at an envisioned strategy, yes, you will decommission a fusion plant, but if you let it stand in place and do nothing with it, it would decay to be relatively non-radioactive in a little more than 100 years. So that is an enormous advantage of fusion. The other feature of economics, again, seldom considered, is when you think about how much have we put as waste into the atmosphere from our fossil fuels. We don't talk very much about the waste from fossil fuels, but in that case, the waste comparison is really stark because that's what is impacting our planet. And finally, still on economics, is that you can consider what we have spent, what the nations of the world have spent over the last 10 years or 20 years or 100 years to position themselves for access to fossil fuels. Think of the armed conflicts. Think of the alliances that have been driven by trying to ensure that my country or my allies have access to petroleum resources. So from that standpoint, the economics of fusion, in which the fuel is readily available for any nation on the planet, that, in an economic sense, says that fusion has really considerable advantages. So fusion in the universe, we won't get into too much plasma physics here, but fusion is why you're here. Fusion is why you live. Fusion is the reason for all of life, for all heat and light on Earth. Fusion is the power at the center of the sun and stars, where at their center, at the center of our sun, for example, with a size, an overall volume, is a gigantic bubble of hydrogen. The size of the sun is about 300 times that, the mass is about 300,000 times that of Earth. So at the center of the sun, the hydrogen, the fusion that is going on, the hydrogen is about 70 times the density of steel. So these particles, which would naturally both be positively charged and push apart from each other, will actually be forced by gravitation. So that's how fusion works in the universe. Like fission, it involves the famous Einstein E=mc² equation in the sense that a tiny bit of matter is converted to a massive amount of energy. But in fact, the fusion reaction is even more powerful than fission. So how do we do that on Earth where we cannot do the same thing that is replicated in the sun? We don't have that gravitation. We cannot fake gravitation by building it into a small, a device that would say be big enough to power a city, into a fusion plant. So how do we do that? You see in the reaction here that we take these two elements of hydrogen, or two isotopes of hydrogen. If you see the orange balls, those represent a proton. Normally, hydrogen is just a proton. But when you add a neutron, the gray ball, it becomes deuterium. That's the far piece. And when you add 2, that becomes tritium. And you may not know these units, but 7 mega electron volts is their entering energy. This is what we get them to in the fusion reaction. And you see that following the fusion reaction, you get 2 products. One is essentially helium. That's a helium nucleus. It's non-radioactive, but if you see the units, it's 5 times more powerful than the incoming value. So that's where you've gained the energy. In addition, you look at the neutron that is produced, it's 14.1 mega electron volts. To compare, if you release that neutron in free space, it would reach the moon in 8 or 9 seconds. That is how insanely powerful that neutron is. So the neutron will collide with the metal walls of the fusion vessel, of the tokamak, the fusion vacuum vessel, and like a bullet hitting a metal wall, if you would feel that, the bullet would fuse and you would feel heat. That's essentially what the neutron does. It transfers its kinetic energy to the wall as heat, and the water circulating behind will then be able to make steam, and in a commercial plant to drive electricity. So that's deuterium and tritium that become helium plus energy in the form of the energetic neutron. What it requires to do this on Earth is that we have a very, very precise magnetic field. And I'll describe that in a little bit. But to get to these energies, we are actually going to, you'll see, 150 million degrees Celsius. The outcome is what we call a burning plasma. That is the goal of Iter. You'll hear me talk about it in a minute. But to look at the particles here, if you see the helium nucleus that has all that energy can still bang into the other particles. It can still energize the plasma, transfer its energy to the plasma, and continue to the point where the plasma, if you have enough of these reactions, the plasma becomes burning or self-heating. And that is what we're trying to do with the size of the Iter reactor. But before I get into the details of Iter, let me talk about where it came from. So this story is fairly famous. You may have heard it, but if not, in November of 1985, you see those gentlemen, Reagan and Gorbachev. That was the Geneva summit, where actually they were focusing on how do we reduce our weapons arsenals, our nuclear weapons arsenals, but they wanted, in addition, an initiative for peace. And this is where Iter came up with as something that would be a benefit for the benefit of all humankind. So quite rapidly after this was at the time of the Soviet Union still, but it started with the US and the Soviet Union. Japan and Europe joined quite quickly thereafter. And it went through a decade and a half of design, of engineering design, conceptual design, engineering design in different locations. Eventually, in the early 2000s, the question came, where will this be sited? Where will it be located? And the decision was eventually reached to place it here in France, where the Iter project is today, but with the participation of all the members. And of course, everybody would have liked to have had, every member would have liked to have had this location with the Iter project on their soil. And in fact, by this time in the early 2000s, you had Korea joining, you had China joining, in 2005, India joining. And so by November 2006, there you have the photograph of Jacques Chirac at the Élysée Palace. And that was really the signing of the Iter agreement. By August 2010, you see there at the bottom left, you have the fields being cleared. And today, this is the Iter site as we see it. And we're going to take you inside some of those buildings to see what it was, how it's really come to fruition. But the key here is that this is really a generational challenge. Why? Because what we today, as adults, have inherited from the previous generations and from our own consumption of energy using fossil fuels is a very negative legacy to pass on to our children. So all of these countries And you can see the names here, China, EU, India. We talk sometimes, you see headlines about trade wars or about other disagreements, even border disputes, many things that go on between these countries. They're the most powerful countries in the world. And yet they are all united here, working side by side, hand in hand in a common cause. Why? Because our generational challenge is to leave a better energy legacy to our children and their children and the generations that follow. So how is Iter going to do that? We can describe the Iter mission in three ways. One is the phrase that you will sometimes see on our website and so forth. Iter is designed to demonstrate the scientific and technological feasibility of fusion power for peaceful purposes at industrial scale, to show that it can be done at size. There have been hundreds of tokamaks built that are smaller. This is the first that will be at the scale that is industrial scale. So we'll talk about why that's so important to all of these countries. The second one I mentioned is the burning plasma or self-sustaining plasma. And to do that, we can reduce the Iter mission to a single letter, Q. Q is the ratio of the output power, the thermal power generated by the fusion action in the plasma versus the heating power that comes in. Why is that important? Because it is a different plasma physics phenomena. Nobody has ever been able to study a burning plasma unless you can count the microseconds of in an H-bomb or being able to study remotely somehow inside a sun, inside a star. So Iter, as an experimental device, is intended to allow scientists to study that burning plasma. For that, we have selected a design that is a Q of greater than or equal to 10 in pulses, or a steady state that would be greater than or equal to 5. Why did we select that? We could have gone bigger, but since Iter is designed as an experimental device, which will go up and go down in power, there would be no point in designing a bigger facility. In fact, it's possible that over time, with stronger magnets, with other things, we will be able to construct smaller machines. We'll see how that goes. That's still in the future. However, the Q that we selected would guarantee that we would have a burning plasma and be able to study that phenomenon. That is why all of these countries are coming together and putting their resources into building the Iter device. So a little more about the engineering of how this all works. It's a series of steps, and we've got them all here. So you put the deuterium-tritium gas into this circular donut-shaped device called a tokamak. You then inject an electric current. The electric current, just like the electric current in a fluorescent bulb that you might see in lighting, it changes the gas, which we think of as the third state of matter, solid, liquid, gas, to the fourth state of matter, which is plasma. What does that mean? It means that the molecules separate and ionize. So the nucleus separates from the electrons. So everything inside there is charged, except, of course, neutrons that will be produced by fusion. So that's the first step. Then you continue heating with electromagnetic waves. And in fact, the electromagnetic waves are very much like the energy that you have in your home microwave, except more of them and, of course, thousands of times more powerful. The final heating system is what we call the neutral beam heating system. It's high energy neutral particles that can bombard the particles in the plasma. And so these three heating devices may or may not be used in the eventual design of the commercial fusion machines, but Iter allows us to test all three and to combine these techniques to reach 150 million degrees, 10 times hotter than the core of the sun, because in this magnetic fusion device, this is the temperature required for those particles to meet and collide. So clearly, at that extraordinary temperature, no material on Earth can withstand that temperature. So that is why we are creating this magnetic cage inside the steel cage of the vacuum vessel, precisely shaped like the steel cage of the vessel, but in a way that will contain and shape the plasma. So this magnetic cage is made up of three main magnet systems. The first one that you see, which is the central column there, is called the central solenoid. That device, and for scale, you can see the human at the very, very bottom. Do you see that? This human is standing there. So this is about 18 meters tall, if you include all of the structure, about 13 meters height of magnets, made in 6 modules. The first one just shipped. I'll show you a photograph later. Just shipped from San Diego. That's being made in the US. Then we have these D-shaped magnets, which you see here in gold. The D-shaped magnets, those are being made about half in Japan, about half in Europe. And then you have round magnets. Since this is a cutaway, it's more difficult to see, but those are the dark red magnets, starting all the way at the bottom. One made in China, PF6, then the next one is PF5, PF4 and 3 here at this level, and then PF2, and at the very top, being made in St. Petersburg, PF1. So by the combination of these ring-shaped circular magnets, the D-shaped toroidal magnets, and the central solenoid, plus, we don't usually show these, but there are also smaller correction coils. So when I say small, the correction coils are on the order of about 10 tons, sometimes a little bit larger than that. Whereas these toroidal field and poloidal field magnets are ranging in several hundred tons apiece, and the central solenoid will be about 1,000 tons in total with its structures. So in combination, that is how we are making this precise magnetic field. Now, I want to talk about the size of Iter. I hinted at this earlier. Why would we build Iter at this size and not larger, not smaller? I said it was because of Q. But Q depends on 3 things, not just size. It depends on magnetic field strength, it depends on plasma density, and it depends on plasma volume. So the 3 tokamaks that you have here, first all the way on the left there, you see Taurus Supra. Yes, so Taurus Supra is now called West. It's quite close to us actually. This is a French tokamak. And then you see Jet. Jet is the largest tokamak that has been made so far. But if you look at these units at the bottom, normally I'm not including this much detail, but this is an important point. If you look at the units at the bottom, you see the volume of the Jet plasma, see there is 80 cubic meters, whereas the volume of the Iter plasma is a little bit more than 10 times more. That size is going to make a huge difference. How? Look at the heating that went into Jet, 23 megawatts, and what did they get out? 16. That's still getting not a net energy across the plasma. You're still getting less energy out than energy in. A Q of 10 means that we're going to put 500, you see here, 500 megawatts of heating for 50 megawatts of heating for 500 megawatts of fusion power to come from Iter. So that's why size matters. Now, if you increase the magnetic field strength, then you could also manipulate that ratio. And there are new magnets on that I'll talk about later in the introduction. New magnets that are out that are also not yet scaled up, but it's possible that you would have stronger magnets which could influence the physical size of the device while still getting a higher output power. However, that would have other influences because, of course, if you contain all of this flux that we have, the neutrons that hit the walls, and you have it even more intensely, then your materials for your walls of the tokamak have to be even more capable of withstanding the neutron flux than those that we will use for Iter. One other thing that I did not mention earlier, we talked about differences in nuclear fission and nuclear fusion. For those of you who know nuclear fission and the fuel that goes in there, you have several hundred tons of fuel in there, uranium and plutonium, something very heavy. We talked about hydrogen being light, but here's the remarkable thing. In this gigantic machine, where the vacuum vessel has this enormous diameter, we're only going to put 2 to 3 grams of hydrogen, deuterium and tritium, in as fuel at any one time. So this is, again, something that says when you wonder how do we have all of this hundreds of millions of years of abundant fuel, that's why. Because fusion uses a tiny, tiny amount of fuel. So let's move on from the discussion of how Iter works and talk first about how we are building it. This next part will be about project management a bit. How is the project managed? And then we'll go on to look at some photographs of where we actually are today in June 2021. So I mentioned that all the members probably would have loved to have had the Iter site on their, the Iter plant built on their land because there are obvious economic advantages. When the decision was made and the Iter agreement was designed, what members agreed on is that they would not simply send money to France or to Europe as the host member, but they would in fact provide in-kind contributions. What does that mean? Components, physical components, right? And that each of these 7 members would have a domestic agency to manage the companies in the industry that would supply these components. The central organization, Iter organization, manages here in Cadarache, and we manage the integration of all those components and the assembly. And of course, a key point, members will share, are bound by the Iter agreement to share all of the intellectual property that is generated by the project. But this makes a very, very unique formula. You've got 7 Iter members, and because of Europe, really you're talking about 35 countries building one machine. And Europe, because it's the host, is responsible for 45%. All the rest, each of the non-European members are responsible for about 9% of these procurement packages. And what I've done here with this graph is to show you a relatively crude breakdown of how all that is. You'll see some of these components being built. But the question is that smart or is that awful? What was that a very smart way to build a machine? The answer is more subtle than you might think. Of course, it means that project management at Iter has to be incredibly, incredibly on tune. How you manage a schedule, how you integrate that schedule. All of these devices coming together have to have incredible precision. In other words, the machine that is built must be incredibly precise. Why? Because no matter how large you build a tokamak, the size of the particles, the magnetic particles that you are trying to contain, don't change. So the weave must be like the weave of your cotton or wool, the weave of a jacket or a shirt or something, a blanket. The weave must be ultra precise so that the neutrons are the only thing that escapes. It has to be able to hold in with the magnetic field all the other particles in order to be efficient. So doing that in a way that has all of these countries and their companies supplying this device and making it all fit together is what makes Iter probably the most complex human endeavor, engineering endeavor of all time. Is it good or is it bad? There are real advantages to doing it this way. And I hope that I can point some of those out as we go through the actual photographs. Now, this is just showing you a schedule. I'm not imagining that you're going to be able to follow all of this schedule, but what you'll see essentially is that where we are here in the middle of 2021 is at the point when a lot of the components are arriving. More will be arriving in 2022, 2023, and then we will be putting these things all together. The current schedule says that we are trying to have all of the system commissioning done by the end of 2024 so that we can actually close the cryostat and have a year of integrated commissioning with first plasma at the end of 2025. Now, we know that there are challenges to that. We have managed to keep going during COVID-19, but we know that there are technical challenges. COVID-19 has slowed down our production rate, but it has not stopped by any means. And as we talk now, we're over 74%, nearing 75% of what we call total construction through first plasma. So that is every 2 months measuring about 25,000 different weighted activities all the way from design through commissioning that will help us to see where we are. So we have been making that steady progress despite COVID-19. Now, there's no float in the Iter schedule through first plasma. And so when you have delays, you have to try to find mitigation measures in some way, do some assembly in parallel, et cetera. But after 2025, you see here a 10-year staged approach. And the staged approach means that first plasma, if we make it in December 2025, would be when you really test the functionality of the overall machine. You don't have everything quite in there yet, and you're just running a plasma with hydrogen, not with deuterium, tritium, and that allows you to make sure that you have a functional machine. After verifying that, you go back to an element of assembly where you add certain pieces. You go then into pre-fusion power operations, and you go through this series of stages with full fusion power envisioned in 2035. And so there is some float in this 10 years following the first plasma. So even if we do now reevaluate what is the post-COVID baseline schedule, and we have to make some adjustments to the slide I showed you earlier, we have every confidence that we will remain on this overall four-stage approach to fusion power operation. So let's talk about making the dream a reality. What does project progress really look like? This is a top-down photo, a little more clear than what I gave you in the first overall photograph of the work site. And as I go through this, I will try to mention some of the Iter members to show you what an integrated international project this really is. So in the Iter switchyard here at this end, many of the components there for the first part of the Iter switchyard, which is the steady state electrical network, were supplied by the United States. There's also in the lower switchyard here, there is the Chinese supplied transformers. There is electrical equipment, really more than a hectare of electrical equipment supplied by others. Then that part of the switchyard, which is called the pulse power network, has input to these two buildings that we call the power conversion buildings that will convert the incoming AC, alternating current, to direct current at exactly the right amperage that it can power the Iter magnets. There's also cryogenic fluid, liquid helium, flowing through the magnets because the magnets have to be superconducting, and to do that, they have to be at minus 269 degrees. So in the tokamak, you've got 150 million degrees, the hottest point in the universe. Inside the magnets that are that are containing the plasma, you have from the cryo plant about 4 degrees from absolute zero, the hottest, the temperature of interstellar space. So those systems are vital to making this all work. Now, you've also got some manufacturing facilities. Here, the PF Coils facility. This is to manufacture the colloidal field magnets that are too large to travel by road. And then the cryostat workshop, the only building on the work site that is owned by India, because India is making the overall thermos that will encase the cryostat, that will encase the overall tokamak. It's being made in 4 large pieces. 2 of them, I'll show you later, have already been installed here in the tokamak pit. One of them, all the way at the top, there is the upper cylinder. That one is finished, but still in storage, waiting for its turn to be installed. And in the cryostat workshop today, India is still putting together the final piece, which will be the lid, the cryostat lid that goes over everything. All of the components from all the Iter members arrive on the work site by that road that you can see at the far. They come on in, they're stored in some of the temporary storage buildings. Eventually, when it's their time, they go through this cleaning building at the back, and then they go into the assembly hall. We'll talk about the assembly hall and all that works. The cranes pick up the equipment, carry it into the tokamak building, and deposit it directly into the tokamak pit. And at the far, you can also see there is the radio frequency building with 2 of the heating systems that will be ready for first plasma. Down here, another heating system, the neutral beam power supply, is being built to full scale now in Italy, and it will eventually come after first plasma as the 3rd of Iter's heating systems. Then if you have heat, if you're manufacturing all this heat and manufacturing with fusion, you have to have a place for that heat to go. In a commercial plant, that would be the turbine generator, right? Which would convert the steam to electricity. Iter will not make electricity, but Iter will have this essentially giant heat exchanger, the heat rejection system, capable of taking far more heat than Iter is actually designed to generate. And the heating system then will make sure that any water before it is returned, we get our water from the canal up above this hill, and before it's returned to the canal, that there is no temperature differential. The other building that I would mention is simply the control building at the far left there. That is still in preparation. I've talked about the tokamak building, but the tokamak building that you can see here is actually 3 buildings in one. Here you have the diagnostics building, then the tokamak building, and then on the far side, the tritium building, which will not be ready for first plasma, but I'll show you a photograph. Work has resumed on that. Tritium building is one of those. And together, the diagnostics building, the tokamak building, and the tritium building comprise the overall tokamak complex. So what have we been doing recently? Much of this now is just from about the past year, maybe a little bit more, where we have been doing installation. The first component, which to be installed in the major component, to be installed in the tokamak pit, is the cryostat base. And you see that right here. This is the bottom of that thermos that I said India was putting together. So that 1,250 tons picked up by these overhead cranes and transported across so that it can be deposited in the tokamak building in the tokamak pit. Now, that might seem simple, but here's something to remember. This is the top-down view as it was installed in the pit. That cryostat base, now on the top-down view, is 30 meters in diameter, okay? So immense. 1,250 tons, and yet the precision with which it had to be stationed in its final position was under 3 millimeters at every one of the metrology points. Why is that important? Talk to an engineer and they'll tell you that that sort of engineering is unbelievable. So what we are doing at Iter, yes, our goal ultimately is fusion power, demonstrating that fusion can be done at industrial scale, but for any type of magnetic fusion device globally, for any project going on, for any national project, for any fusion roadmap that any country has, Iter is providing value by proving that fusion engineering can be done at full scale. The next component, the cryostat lower cylinder. So again, this is the thermostat, and this is essentially just a circle of metal, but an incredibly precise circle of metal. Again, 30 meters in diameter, the same as the base, 10 meters high. That essentially means that this component was about the size of the prehistoric monument at Stonehenge. Yeah, the ring at Stonehenge, if that gives you perspective. And again, that was lowered in just a few months after the cryostat base. In January, we lowered another component, which we sometimes talk about as the jewel. There are multiples of these. This is a very, very shiny component made by Korea. It's the thermal shield comes in two types. This type is insulating the thermostat from the cryostat from the interior of the tokamak, and it's metal, but with a silver plating that helps it to be ultra reflective. I'll tell you about another one a bit later. But we don't always talk a lot about Iter innovation. And here's a good example where Korea is using the insights. They're making the thermal shield. They're using the insights that they took from manufacturing the thermal shield to improve shipping containers for liquefied natural gas, which again have a similar parameter, which is you want to keep the cold in and the heat out. And their experience in working on Iter helped them with perfecting that. Now, on the top picture on this one, you see us getting ready to install Iter's magnets. This was early 2021, several months ago. Actually, most of the welding was finished even in the last few months of 2020. But this is where the welding had to be completed, where we're putting the first two components together, the lower cylinder to the cryostat base. So really about 90 meters of welding done partly by humans and partly by robots. The first magnet was installed in April. This is poloidal field coil number 6. And you know, you're going to see another photo of this later. So remember PF6. PF6 doesn't look so big here, right? Because it looks like it's kind of small, you know, sticking into this. But that magnet is 10 meters in diameter. It's huge. It's incredibly weighty. It was procured by Europe, but Europe procured it in China because they were doing many PF6 magnet or multiple PF6 magnets at the same time. So there you see PF6 as the first magnet installed in the pit. Now we talk about vacuum vessels. The vacuum vessel in Iter is like the sections of an orange. If you think about how you cut an orange into sections, each of the Iter sections is 40 degrees, in total making up 360 degrees. And there you see on the top left the vacuum vessel sector number 6, the first one to arrive. With on the back, you can see that there are these parts of it that are sticking out in the back. That is the port plug supplied by Russia. And then to make an overall subassembly, you need two other things. You need toroidal field coils supplied by Japan and Italy. In this case, you see TF12 in a tool specially made by Korea, which would be able to upend the magnet so it can be placed onto the giant assembly tool with the vacuum vessel. And there's another piece, which is this thermal shield. Now remember I said it was silver coated? The thermal shield that was round that you saw earlier is providing insulation inside the cryostat. This is another layer that goes directly around, conformed precisely to the vacuum vessel sector. And here you can see that a piece has been added on to the first. This is the same vacuum vessel sector, but a bottom-up view. So then you have the cryogenics plant and system. There are a bunch, we talk a lot about the tokamak and what goes inside. But across the Iter site, you have a lot of engineering going on that is of incredible precision also in order to make the overall system work. So the cryogenics plant and system is both a physical facility. We will be circulating about 25,000 tons of liquid helium using this, plus quite a large volume of liquid nitrogen as well for some of the other cooling components. And that requires not only the central plant, which kind of looks like if you open the back of your refrigerator, tanks, compressors, valves, pumps, etc. And it also involves the lines. So all of these cryostat lines have to be precisely maneuvered all the way through from this plant into the tokamak complex. A note on global progress that I said I would refer to, I mentioned it slightly earlier. There's a lot of R&D going on what we call high temperature superconducting magnets. So those would be magnets that would only need to be cooled to about -70 degrees. A little colder than your refrigerator or freezer, but still it would not require this gigantic cryogenic system. So there is an example of where globally the fusion research community is working on ideas that could help to further optimize the machines of the future. Now, Christian Lünig, who is a German photographer, took this photograph of the cryogenics plant. That's just a more artistic view of the plant that you just saw. I'll show you a couple of his photographs as we go forward. Electrical networks. So I mentioned these already. I won't go into too much detail here, except to say that the photograph you see at the top left is actually the steady state all the way at the back. That's the steady state electrical system, which is converted to the French grid. That's powering all the Iter buildings. It's the normal system. And then we have what we call reactive power compensation. And the reactive power compensation system is the pulsed power system, essentially, that is able to deliver a much higher amount of electricity, but in a microsecond. And it's not needed throughout the plasma reaction. It's needed only for a burst at the beginning. And so the overall energy used, if you think not in terms of kilowatts, but kilowatt hours, the overall energy used is not that great because it's a microsecond, but it still requires the installation of almost a hectare, probably around a hectare, of this specialized equipment for the pulsed power system. Magnet power conversion, I mentioned this next. So the power that is converted from AC to DC has to power the magnets. And so these yellow bars, these giant bars that you see, go all the way through these buildings, and also inside the tokamak complex, where these bus bars supplied by Russia carry the electricity DC, direct current, at the amperage and voltage needed for the magnets. So both inside these buildings and in the bays that are on the outside, we have components from China, India, Korea, and Russia that are all coming together to make the magnet power conversion. And I could have made this point here in orange in several of the slides, but I would mention it here. One of the other benefits of the Iter project is that we are in fact creating a worldwide network of companies that have experience in meeting these insanely demanding requirements for fusion engineering. Important point, important contribution of the project. Here another photo by Christian Lünig showing you a more artistic version of the magnet power conversion building on the inside. Now here we have the heat rejection system. I mentioned this already. Basically that large building at the far left is just, it's a giant heat exchanger, but then it is also, there's a network of piping and so forth that is able to take away well more than the 500 megawatts of heat, thermal power, that is Iter's design, plus Iter is scaled to maybe go up to 750 megawatts for future experiments. So we have, with 1.2 gigawatts, more than enough capacity. This gives you a Christian Lünig view of that piping system, again, an artistic rendition. And on the top of that heat exchanger building, almost an oil painting, but this is actually a photograph, showing the Indian supplied fans at the top of the building. Also inside, there are the cooling basins, which provide the gigantic capacity that I was just talking about, the removal of all of this heat from the Iter tokamak. Delivery. Delivery is quite important. Remember I said that little magnet, quote, PF6, doesn't look very big when you see it being installed. But on the photograph at the top right, you can see that in fact PF6 at 10 meters is a huge, huge load to come up the Iter itinerary. All the components arrive in Marseille at the harbor, and then they have 104 kilometers to travel all the way up to Iter. And we're shutting down the road at night in order to make that happen. In fact, a couple of years ago in the summer, when we saw that this component was going to not ship on an angle but ship flat, we moved, we actually asked the local authorities, and they removed a little bit more of the cliff to allow passage of this component. So yet another contribution of the Iter project is understanding the complex logistics that are designed to deliver these massive, very, very high precision components that are very temperature sensitive from 3 different continents. And that has proven reliable even during COVID-19. Why is that important? Because to be honest, while many countries are looking at doing their own demo plants, when you're doing them at industrial scale, there still is no country on earth who could do all of this work by itself. So the ability to create that global logistics supply, the global supply chain and the logistics for how to deliver things is quite an important Iter contribution. On-site fabrication, we've been, as I said, making the coils that are too large to be shipped, making them here. Now the one at the top is the one you've seen twice before. This is PF6, but this is PF6 after it arrived and after we took off the packaging and did the cold testing. And then these two, which are large, that one's 10 meters. I know it looks larger in the photo, but this one here, PF5, after it was done, is 17 meters. And just to show the contrast, we temporarily, after it was finished, put it inside one of the quote, quote, pancakes, the flat layers of PF4, which is 24 meters. So these are the ones that are being manufactured by Europe on site. Now, India is also doing some on-site fabrication, as I mentioned earlier. Here you're able to see the components of the cryostat lid, which are, as they arrived and as they were stored there in the hall, they're arriving from India, and then they all have to be put together and welded here. Why is that important? Well, it's a great, great example of multinational cooperation. These things are forged, these pieces are forged in Hazira. They're being welded together on the Iter site by German experts, German welding experts, under Indian supervision and French nuclear regulation on an international site. And that's just a microcosm of how Iter really works. Here you see the actual welding starting to give you perspective of how big that is as these pieces of the cryostat lid are fabricated together. There's lots more manufacturing ongoing globally. We're at about 85% of all Iter's manufacturing being done. This is not by any list an exhaustive list of the components that I'm going to give you for each of the countries, but it will give you an example. So in Europe, as I mentioned, Japan and Europe are making the TF coils, so there's some of the European TF coils being made. We mentioned that Korea had sent a vacuum vessel. Europe is also well along in completing the 5 of the 9 vacuum vessel sectors, which right now are about 67 to 89% complete. And that also, with the human standing in the middle, shows you the massive size of these precise components. Russia, to give you an example, is working on that top magnet, similar in size, a little lighter than the one that was shipped by China. This is PF1 in very late stages of fabrication. Just actually earlier this month, Japan celebrated the completion of the number 5 coil, which was made by Toshiba. Mitsubishi had been making the others, and Japan has 4 more of these toroidal field coils in manufacturing. I mentioned, I showed you the art photo of this piece actually installed, the cooling tower fan manufactured by India. India has actually manufactured quite a lot of the cooling water system components. And on the vacuum vessel sector, again, here you see a view of where Korea has welded these Russian-made plugs onto the outside of its vacuum vessel sector, the second sector, and is about to put this sort of shipping house over top that is now actually on its way to Iter. China is delivering a lot of the feeders, which are actually tokamak building components that do the final delivery of the electricity and the heating, the cooling, the cryogenic cooling for the magnets. So lots and lots of that arriving. They're in series production now. They've already delivered quite a lot of it. And just earlier this month, the United States shipped the first of 2 completed modules. There are 7 modules overall for the central solenoid, 6 to be installed plus a spare. And they have completed the first 2. The others are in advanced manufacturing. And this one is actually now, as I speak, on its way between San Diego and Houston, where at the port of Houston, it will be shipped to Marseille to become the first central solenoid module here at Iter. Now, I'm about to close, but I want to mention other fusion projects going on because sometimes we get questions about that. First of all, there are other ways to do fusion. There is inertial confusion, which is inertial fusion, that was a slip. Inertial fusion is something that uses lasers to produce a very concentrated burst of fusion at a defined point. There is a combination project that's kind of a mix between magnetic confinement fusion and inertial fusion that's being done by General Fusion, which just announced they're going to build a plant in the UK. In the world of magnetic confinement fusion, you have generally tokamaks and stellarators. Iter is a tokamak, and the tokamak has the most research of any of these models. That's why any of these approaches, that's why it's been so heavily researched. That's why Iter is a tokamak, because it represents probably the most reliable, well-studied way to producing commercial fusion. The largest fusion plant I mentioned before, you saw an illustration of it, is JET. There is an MIT spinoff that is looking at, for the Massachusetts Institute of Technology, that is a private venture. This is also a private venture, Tokamak Energy in the United Kingdom. These are private projects, and people always ask, are they going to make you obsolete? Are they going to go faster than Iter? And the answer is sure. Private investment, private initiatives don't have some of the restrictions that public funding does if you look at procedural things. But from a physics perspective, they've got the same challenges that we do. And it is not, it can be, if you're a private investor, it can be a competition, but we don't view this as a competition. We are all working globally, private sector now entering the race, which is a fabulous sign saying we're getting closer. We are all working to exactly the same goal, to try to address this generational issue that I mentioned at the beginning, the need for massive carbon-free energy. So from the standpoint of governments, Iter will be followed by demo, a pilot fusion plant. You've got some Iter members that have announced plans, or in some cases are well along toward the conceptual design or the engineering design for their own pilot plants. And as I mentioned in the previous slide, private industry is beginning to invest in fusion energy initiatives. So that's it. Thank you for your attention. I give you this final photoshopped photo that shows that Iter, as building a star on Earth, is taking its place here in the Milky Way among the stars of the universe. If you would like to take an extended tour of the Iter worksite from just a couple of weeks ago, there's a video that will actually take you into some more detail inside the buildings that I was showing. I hope that I've provided you a good introduction to the overall Iter project. And we invite you also to sign up for visits. There's a visit, if you come here to Cadarache, to the south of France, we will do our best to introduce you physically to the Iter project. You get to see it at scale. We also have virtual visits available. We hope that you will continue to follow our project as we really seek to make a complete difference in how energy is produced by future generation in a way that really makes a contribution to carbon-free energy for our children and future generations. Thanks so much.